For our next topic, we're going to talk about the idea of a type system. As we've discussed before, programs can have many different kinds of errors. For example, they could have an error that would be like, I write the program, I write return 1 plus, and then a semicolon. This is an example of a syntactic error. It's an error that is not really an error about a program, it's an error about your attempt to write the syntax for a program. This string right here cannot be turned into a tree for our programming language, so therefore this thing right here is not a program. It's not a program with an error in it, it's just not a program at all. Other kinds of errors could be like a logic error, where my program says return 42, but it was supposed to be return 41. This is a kind of error that is not really an error from the perspective of the programming language, but it is an error from the perspective of you, the user. There can also be errors like applying partial functions. For example, if we were to do something like 1 divided by 0, or if we were to try to take the first of empty, these things don't make sense because the operation is not defined. Like division is not defined with 0 as the second argument, and first is not defined on an empty. There are also what are called so-called type errors. Type errors. For example, if we were to try to take the word for and add that to 1. Now, each one of these are interesting errors. Syntax errors are, of course, a whole category of problem that if we were to study parsing, we would spend a lot of time talking about identifying ill-formed syntax and trying to give helpful error messages. And you, as a programmer, like to have good error messages from your parser so that you can make sure that you're not making mistakes in your program. Similarly, it's really important to not make logic errors in your program so that you do what you want to do, right? In my class, a logic error would be writing the wrong program, and then you get a bad grade, and you don't like that. If you have a real job, then a logic error means that your boss is unhappy with you, and so on. Partial functions, we've talked about how in some ways they can be a little bit unavoidable because it's hard to know whether or not you're going to happen to do a division by 0, and that's why exceptions are often built into languages so we can handle that. Type errors, though, are special. And in practice, the reason that they're special is basically because it is possible to automatically determine their presence. Automatically determine if they are not present. If they are not present. So there's a little bit of a fuzziness between these three different kinds of things. What makes a type error versus a partial function versus a logic error? And essentially what we're going to say is that something is a type error if it's possible for us to determine if such an error doesn't exist in your program. So let's take a little bit of a diversion into what it means to make a prediction. Okay, so type systems predict if your program won't have a problem. Notice that I'm not saying it predicts whether your program will have a problem. It predicts whether it won't have a problem. So we're going to use the word theory to refer to predictions. And we're going to use the word model to refer to real phenomenons. Real phenomenon. And here is, we're going to use a little notation. We're going to say that X, this is called a turnstile, P, means that the theory X predicts P. And then we're going to say Y, and then this is a double turnstile, Q. We're going to say that the model Y, that's the right word, not predicts, we'll say performs Q. So here's an example that I think will be familiar. So we might say that gravity, and when I say gravity, I mean the Newtonian theory of gravity, so Newton's gravity, it predicts that my pen will drop. Okay, so watch. Okay, so Newton's gravity predicts that if I take this pen right here and I drop it, right, I let go of it, then it's going to fall and touch the tablet. That is a prediction that a mathematical theory can make. Now the question is it the case that the universe itself also performs that action? Is that true? Well, we have the universe right here. Let's see what happens. I'm holding it, now I drop it, and bam, it falls down. So the answer is yes. So they both say yes. In this case, the theory and the model agree. Now there are two different ways in which theories and models can agree. The first way would be when for all P, if a theory predicts P, then that implies that the model will actually exhibit P. So what this says is that if gravity predicts something, then it will actually happen in the universe. There's another kind of connection between theories and models, which says for all P, if the model exhibits something, then that means that the theory predicts that thing. Okay? So what this means is that if I take out some math and I write down, I think this is going to happen with gravity, and I solve the equations, and then I go run the experiment, the universe will have the same thing happen. That is called soundness. When a prediction does not make false predictions. Because the alternative of that would be I take out my math and I figure out what gravity is supposed to do, and then I let go of the pen and it floats up. Okay? So that would mean that my theory is wrong. Alternatively, what does this mean? This means that anything that I actually see in the universe, meaning that some experiment that I naturally observe, my theory has an explanation for it. This is called completeness. If you have a complete theory of gravity, then if you look around, then any experience that you happen to observe, your theory can explain that. I am not a physicist, but my understanding is that neither of these things are true for our current theory of gravity. On the one hand, our theory makes predictions that are false when the values are very, very small or the densities are very, very high. And this is one of the reasons why we cannot use our math to predict what happens inside of black holes. So that means that our current theory of gravity is not sound. It makes predictions that we do not see in reality. Similarly, it is not complete. And the reason that is that we observe things in the universe. For example, we observe that galaxies are a certain shape, but our theory says that they can't be that shape. Now, we then modify the theory to include dark matter, which we have no other explanation of. It's basically just something that we add to our theory to make the theory match what we observe in the universe, and we call that a new model. But really, we don't have any way of predicting what exactly dark matter is or what other phenomenon it would have. So when we add things like that that are yet to be explained, that's an indication that our model is incomplete. All right, so we've now talked about soundness and completeness generally. So now let's apply those concepts to programming languages. Our program is a model. It has certain behavior that it will actually perform. There are certain things that it will actually do. And what we would like to do is we would like to predict what things it will do. We want to predict what it does. What it does. I.e., we want to build a theory. Build a theory of what programs do when they get run. Once we have this theory, we're then going to predict whether or not our program runs and has an error in it. We're mainly concerned with the idea that when we run our program, it might have one of these problems. It might have a problem like a partial function, a logic error, type error, etc. Okay? So if we could predict that, then that would be useful because we would know whether or not there was going to be an error before we even ran our program. This is only useful if making the prediction is faster than actually running the program. So we're going to say useful if prediction is faster than model. For example, I've written a program, and there's a function in there that takes, I wrote a program, and my program is going to take as input a number that you type in at the command line. I don't know what number you're going to type in. I want to predict anyways what it's going to do. If I can get any prediction in that, and if that prediction is accurate, then that would mean that I would know what my program was going to do without you having to even provide the answer. That means that my prediction is faster because I can get the answer right now, even though you're going to provide your number in a year from now when I actually give you the program and you finally get around to running it. So that's one notion of faster. If your program doesn't take any input, maybe when I run it, it'll take 2 years to run. But if I can make a prediction about whether it's going to have an error, maybe I can do that prediction in 1 day. And in that case, that's going to be good because I don't want to run your program for a whole year, and then maybe after 9 or 10 or 11 months, maybe like 11 months and 20 days, like a week before it's going to be done, then there's finally an error. That would be terrible, right? Because I would waste all this time. So if the prediction is faster than the model, then it's useful. Okay? Now, it's also useful, it's only useful if it's sound. And sound. Because if I make a prediction about what your program is going to do and it's not sound, then it's useless. It doesn't matter, okay? Because, yeah. However, we can get away with not being complete. Now, what does that mean? Imagine that your program actually is good, meaning it actually doesn't have an error. But I predict that it has an error. That's not so bad because then I won't be able to run your program. I won't run your program because I'll think it has an error, but it doesn't actually. What would be really bad if I thought your program didn't have an error, but it actually did? Well, that would only be the case if it was unsound. So we're going to say it's okay if not complete. Now here's the next thing, and I'm not going to go into the great detail about why this is. There's a whole class on this, the Foundations of Computer Science class. It turns out that it is impossible to be both sound and complete. So both are not possible. And that's called the Gödel incompleteness theorem. Incompleteness theorem. And it is related to the halting problem. Okay, so what does that mean? That means that there's a space of programs. So here are all possible programs. Many of those are correct. However, only some of them our theory says are correct. And we'll call those programs typed. Okay, so typed equals our sound theory says they are okay. And there must be a gap between these two things because of incompleteness. All right. I'm just telling you what type systems are. We haven't really explained how they work or anything like that. We're just talking about the structure. And this is actually a very important point. Because what this says is that if you use a type system, you are saying, I don't want to write a program here, I want to write a program there. There are many people who have very strong opinions about whether you should use a language that has a type system or doesn't have a type system. Roughly, those arguments are, you should use a language with a type system because you want it to be correct. These people do not understand that not all correct programs are typed. And therefore they are sort of, what's the right way to say this? They're like fetishizing the type system as being the only arbiter of correct programs. However, they have the advantage of knowing that their program definitely is correct, at least as far as all of the kinds of predicted errors that the type system predicts. And we'll talk later on about how there are all sorts of things that type systems don't typically predict. Okay, people that don't like type systems, what they say is, it's so much easier to write your program, you don't have to satisfy this annoying type system. Essentially what they're saying is they're saying, I want to have all this room to move around in. I want to write my program right here or write my program right there. I don't want to be forced inside of this little box of what is acceptable to the type system. And the flexibility of moving around this space is very desirable for them. Okay. Now, wouldn't it be great if there was some way to merge both of these things? So doing that is called gradual typing. The idea of gradual typing is that you have a program that, so here are the typed programs, okay? And here are the correct programs. I put the circle on the wrong side. And here are the correct programs, all right? And then what gradual typing allows, and then of course there are all programs. What gradual typing does is it says, you can write a program that sits in this region right here. And what we do is, your program has two parts. It has a typed side, and then it has an untyped side. And they communicate with each other. Now this untyped side, it might be correct or it might not be correct. We don't actually know, and we don't know because it's we're not saying anything about whether it's correct or not because it's hard to know. We'd have to use some other process for figuring that out. Okay, and what gradual typing says is that every time the typed side sends a message to the untyped side, it's not, so if there's an error, we'll say that errors are untyped's fault. And if the untyped side sends a message to the typed side, then again, errors are the untyped's fault. Okay? So the idea here is that we can write a portion of our program in the type system, and we know that it is following all of the rules that satisfy our prediction engine. And there's an untyped part that doesn't have to do this. There are many implementations of gradual typing. Typed racket is one of the first ones, but there are others like TypeScript and Hack and reticulated Python and CoffeeScript. There are many, many options. The core idea between these programs can be expressed inside of an operation called typed that takes an expression, and we can think of it as expanding to E after checking with the type checker. Okay. And then there's another expression that's called untyped, TE, where what we do there is we call protect, that's the thing from the contract system, where we're going to protect this value E, and we're going to assume that it's supposed to be of type T, and if it's a failure, then we know it's the untyped's fault, and otherwise we know it's the typed's fault, and we know that it's never possible for it to be the type's fault. All right, I'm going to elaborate on these ideas later. But I just want to talk about the overall structure right now. All right, so now what exactly do one of these predictions look like? Recall that we're going to make something sound. So to make something sound, we're saying that for all P, when the theory says P, that implies that the model exhibits P. Okay? What is the theory and what is the model? The model is going to be the derivation of running our program through the small step semantics until we finally get a value. That's what it's going to mean to model, where the value is in some set. And the theory is going to say, given some program E, I predict it will be in some set. So we're going to predict which set of values the value that comes out on the other end is. Let's look at a really, really simple programming language that's not our big J language. We're going to go back to basics and talk about a really simple language, and then we'll build it back up. Let's suppose that E is equal to either a value, an addition, a less than, a not, or an if. Actually, let's skip if. Okay. Now, a value is either going to be true, false, or a number. All right. Now, what are these sets that we're predicting it's going to be in? These sets are called types, and we write them down with a capital T. So the types are going to be the type bool and the type number. Now what we need to do is we need to write down what the real rules are. Okay, so I imagine that you can figure out what the rules are. So the semantic says that we're going to have our evaluation contexts are either going to be a whole, they're going to be a plus E, or a plus VE, or a less than EE, or a less than VE, or a not E. And you can imagine what the other rules are. But now, how do we say what these values are? So we're going to say that true, we're going to model true as being a bool. So this says that the model says that true is a bool, and it also says that false is a bool, and it says that all numbers are num. So this right here is our model of what it means to be, of what it means for V to be in some set. Next, we need to write down the theory, the predictive theory. We're going to write down the predictive theory using inference rules. Inference rules look like this. We have a bar with a conclusion on the bottom, and then we have conditions on the top. For example, here is an example inference rule. We could say, is raining, and am outside. That implies am wet. Okay? This inference rule may not actually be true, right, because I could have an umbrella. There's also for ways I could be outside and not be wet. Okay, maybe we could define being under an umbrella as not being outside. But here's an example. If these two conditions are met, then that conclusion is true. Now, sometimes when we write inference rules, we use variables. So we'll say something like, if x is equal to 0, then that means that x times n is equal to 0. And we are implicitly saying this is true for all x and n. We typically don't write this for all, but whenever we see variables in an inference rule like that, we know that those are for all. All right, so here's our predictive theory. Our predictive theory says that I predict that true will be a bool. I predict that false will be a bool. And these have no conditions on them. I also predict that a number n will be a number. These predictions perfectly match the model because they're on basic values. However, the next ones are going to be more interesting. We're going to say, if I predict that E1 is a number, and I predict that E2 is a number, then I predict that plus E1, E2 will also be a number. If I predict that E1 is a number, and I predict that E2 is a number, then I predict that less than E1, E2 will be a bool. If I predict that E1 is a bool, then I predict that not E1 will be a bool. This right here is a predictive theory about what happens when we run programs in this language. Okay. This is not an algorithm, so not an algorithm for determining whether or not any particular program this is not an algorithm for figuring out what a prediction is. It is just a set of rules for specifying what a valid prediction is. Let's look at an example one, and we will come up with, we'll implement an algorithm using our brain. So, imagine that I have the program not less than 1 plus 2, 3. Okay? And I would like to make a prediction about this. Well, let's go and let's just label these rules. Let's call this rule A, rule B, rule C, rule D, rule E, and rule F. Okay? Well, this is a not, so that means that we're going to use rule F. So what rule F says is that we can predict that this is a bool if, and now I'm going to write the bars in the opposite direction, if we can predict that less than 1 plus 2, 3 is a bool. And we can predict that via rule E, if we can predict that 1 is a number, and we can predict that plus 2, 3 is a number. Well, we can predict that this is a number using rule C. And there are no additional conditions, so we're done there. This one we can predict using rule D if we can predict that 2 is a number, and we can predict that 3 is a number. We can predict that this is a number based on rule C, and this is a number based on rule C. So we can apply these rules in this order and derive a prediction that this program actually evaluates to a bool. Now let's see if that's actually right. Well, we'll have not less than 1 plus 2, 3. Okay. Well, the first thing that's going to happen is that this is going to reduce to 5, so we're going to get not less than 1, 5. Then we're going to get not true. Then we're going to get false. And does the model say that false is a bool? And the answer is yes, it does. So therefore, we correctly predicted what this program will do without running it. Good for us. That means that what we have done is we have made a sound theory. Now, let's take what we just did and try to write it as a program. Write the prediction program, that is. So we're going to write a function called typeOf. And what it's going to do is it's going to take an expression and return a type. And this is going to be an algorithm that's going to run and predict things. So if we call typeOf, and we give it a bool b, then we're going to return bool. If we call typeOf, and we get a number n, then we're going to return number. If we call typeOf on a not of some expression e, then what we're going to do is we're going to say case typeOf e of bool goes to bool. Number goes to error no type. And maybe we can make a nice error that says, I couldn't construct a type because I expected it to be a bool, but it was actually a number. Then we can say type of add e1, e2. What we're going to do there is we're going to say case type of e1 of number goes to case type of e2 of number, and this returns number. If it's a bool, then we'll error. And then if this is a bool, then we'll error. Okay? Now obviously the rule for less than would be just like this, except that num right there would say bool. So this program right here, typeOf, this function, what it does is it takes an expression and it actually makes the prediction. Okay, this is cool. We can make our program much more obviously powerful if we change our language to have one new feature. We'll add a feature that's called read. And what read does is it's going to read a number typed in by the user. Okay? We're going to add a rule that says read is always a number. We're going to add a case that says typeOf read is equal to num. Now the thing that's cool about this is that we can predict that not less than read plus 2, 3, we can predict that that is a bool and will never be wrong, because read, by definition, always produces a number. So we know, via the model, that it always produces a number. This is an example of how what a type system can do is it can let us make predictions about things that haven't happened yet. All right, this is a really basic type system, but we can still talk about what it means for it to be correct. what we would like to do is we would like to prove the soundness theorem. The soundness theorem basically says, for all expressions and all types, if we predict that that expression has a type, then that implies that there exists some value v where if you run e over and over and over again, you'll get some value, and that value, its type will also be t. This is an example soundness theorem. And we could prove this based on what we've written so far. However, it's not always possible to prove a soundness theorem like this. And here's the reason why. Sometimes when you write programs, they don't actually complete. There is no value that they evaluate to, because you might write a program that is supposed to run forever. For example, maybe you wrote a program that was like a web server. A web server isn't supposed to stop, it's just supposed to keep going over and over and over and over and over again. So in that case, we can't use a theorem like this. Instead, what we do is we write a theorem like this. We write two theorems. One is called the progress theorem, and one is called the preservation theorem. And here's how it works. The progress theorem says, for all et, if the theory predicts that e is of type t, then that implies that either there exists an e prime where e gets turned into e prime, or e is a value. Okay? So progress essentially says if something is typed, then that means you can run it one step and it will actually run. Meaning that it won't have any undefined behavior, it won't get stuck, it won't stop running, it won't be partial, etc. And preservation says, for all e, t, and e prime, if we predict that e has type t, and e runs and turns into e prime, then that implies that we would also predict that e prime has type t. This tells us that if something already has a type, meaning we already predict what its type is, and we know that it actually runs, then that things that it turns into has the same type. Let's look at that applied to this example right here. We predicted that this thing had a bool. We would also predict that this is bool, and we'd predict that that is bool, and we'd predict that that is bool. The progress and preservation theorems more robustly express what we want out of soundness. We want to know that when we run, that if something has a type, it doesn't have an error, meaning that we can actually run it. And we want to know that if it does run, it has the same type as it did before. And the progress and preservation theorem can be appropriately applied to programs that run forever. They will continue to have the same type over and over and over again. All right, we've only covered the very basics of type systems. We've talked about their basic structure, some of their basic issues, but we've only done it for a really basic language. A basic language made up of only a fixed number of operations, plus, less than, and not, and the read operation. What we'll do next time is we'll start expanding this way of thinking about type systems to our actual language so we can talk about all of the interesting things that we've covered so far, but applied to real type systems. All right.